Okay, so the last aspect of the equilibrium topic, and probably the most relevant one for the next topic, acids and bases, is doing calculations within equilibrium. So doing calculations with Kc and understanding how concentrations are going to change and how to solve for them. So there's a couple different types of calculations you could see. The first couple are very simple, so you might have to calculate a value of Kc, which we should have already talked about if we've talked about the equilibrium constant and Q. And all this implies is you set up the correct equilibrium constant expression and you plug in concentrations. So that's pretty simple. If this was our equilibrium that we're dealing with, all coefficients are 1. So down here, this is the Kc expression. Given all the equilibrium concentrations, you can plug them into the corresponding spot, do a little calculator solving, and you get this as the equilibrium constant. You obviously have to solve for the units, which we've gone over previously, so I'm going to skip past it for now. The second type of calculation is also pretty much just plug and chug. If you plug in, you've got the Kc value, and you set up the Kc expression, then you're just solving for x. You're solving for an unknown. So in this case, they've asked you to solve for the H2 concentration given Kc, NH3, and N2. So I've set it up a little bit more rough this time. Here's Kc. On top, I've got the product, NH3, being squared because of its coefficient 2. And on the bottom, I've got the concentration of N2 raised to the first power because coefficient 1. And then the one we don't know is hydrogen, so that's being raised to the third power due to the coefficient of 3. I very quickly have done the algebra to get x by itself. So I've got Kc now on the bottom over here and to the third power. Again, this would obviously be math you do with a calculator. And so you can solve for the concentration of H2. Here's another example. Now they've given you, or this is like the first type of calculation. They give you some new concentrations, plug them in to the expression, and you get Kc. And so a follow-up question would say, the Haber process is exothermic. Based on the two Kc values, can you figure out whether or not this second Kc was at a higher or lower temperature than question 1? So the key there is comparing the two Kc values. The first Kc value is, and again, when you compare them, the most important thing to compare is their exponent, because they will try to trick you sometimes. By giving you a larger number here, but then the exponent's actually smaller. So in this case, we'd be comparing -3 to -6. We should be able to see that, therefore, Kc has decreased. And if Kc has decreased, that implies that the system has shifted to the left, because we've made more reactant, more of what's on the bottom of the fraction, the Kc expression, and less of what's on the top. So a shift left, and of course this is with temperature, because temperature is the only stress that actually changes the value of Kc. So whatever just happened with temperature made us shift left. Well, if the Haber process is considered to be exothermic, that means that the forward reaction is exothermic. So we know based on the Kc values that we shifted left. And so if the forward is exo, then the backwards must be endo. So that's one piece to figure out. We've just shifted left. Left is endo. And from your Le Chatelier's principle, you should know that the type of temperature change that favors endo is a temperature increase. So a lot of steps of reasoning. These temperature Kc questions are probably the most challenging. They take a few steps to think through. But given that the forward is exo, you should know the reverse is endo immediately. You've seen that the Kc has gone down, which implies a shift left. So you know you've shifted in the endothermic direction because left is endo. And you know from before that an increase in temperature always favors the endothermic direction. Therefore, the second Kc is being measured at a higher temperature than the first Kc. So a couple different lines of reasoning, but eventually that's all pretty logical. The main point of the video, though, is to go over what we're going to call ice calculations. And in honor of that, no, not this. Oh, why did I lose that? There we go. Not sure if you can hear this in the video, but I am now listening to Vanilla Ice, Ice, Ice Baby, because we're going to do our ice calculations. It's going to be horribly distracting, but we're going to try to get through it. So the key is to set up the reaction. All right, I am going to have to stop. Sorry, Vanilla. We'll listen to that in class. You're going to set up the equilibrium reaction, and you're going to focus on initial concentrations, the change in concentration, and the equilibrium concentrations. Usually, in equilibrium, you can't actually measure the concentration of everything, but you can try to figure out the concentration of one thing. And so if you know where you started and then where one thing has changed to at equilibrium, you can figure out how much it's changed, and you can apply that change to everything else in the reaction. So it's best understood with an example. We'll start with a simple one. All the coefficients are 1. This is sort of a classic equilibrium that they'll use on the IB exam. So let's say that initially the reaction begins with 1 molar PCl3 and Cl2 and no product. Kind of logical. Oftentimes you'll start with no product. So we would set up the I of the ice calculation. We put the concentration beneath each substance in the reaction. So that part's pretty simple. It's really just reading the question and putting the numbers in the appropriate place. And let's say the question then went on and said, at equilibrium, the concentration of Cl2 is measured to be 0.16 mole per dm cubed. All right, so based on that new information, that's an equilibrium concentration. So we're going to plug 0.16 in for the E value, because we're told one equilibrium concentration. And based on that, I can figure out what C is. C is the change. And so if I started at 1 and I'm ending at 0.16, then the difference is the change. So the concentration of Cl2 has gone down from where it started to where it is at equilibrium by 0.84 molar. Okay, well from that we can figure out what the other changes are. If we call the change X and we pay attention to the mole ratio, which is 1 to 1 to 1, that means that in this reaction, all of them are going to change at the same rate. So however much Cl2 goes down, PCl3 is also going to go down by that much, and PCl5 is also going to go up by that much. So first off, we know that the magnitude of each change is the same. They're all just going to change by X, and that's just because of the mole ratio, 1 to 1 to 1. I always use up one of each of these when I form one of those. The sign I'm figuring out based on the first one. I know that the chlorine has gone down from 1 to 0.16, and chlorine is a reactant. So that implies that this reaction is shifting to the right, which means all the reactants should be going down, and any products should be going up. So I'm going to apply a negative sign to any reactant change and a positive sign to the product change. That's why it's negative X for both of these and a positive X for the PCl5. Since I know, if I look back at the previous page, that we changed by 0.84, chlorine changed by 0.84, since that is X, or that's really, X is 0.84, and for chlorine it was minus, that's why it went down to 0.16. So now I'm just going to plug in that change for everybody. I will edit this to make it say minus and minus. Okay. And so I've got minus changes happening to both my reactants. I've got a positive change happening to my product. And so I just apply the changes, and now I have all the equilibrium concentrations. So now, this goes over in some writing about what I just said about the negative and positive. Now at the end, all I have to do is plug these three concentrations into the Kc expression, and I get the equilibrium constant at this temperature. So a couple extra steps, but hopefully it's pretty logical. Let's try one more example with some different mole ratios. So a 1 liter container, you're given the moles of both reactants. You're usually led to assume that there is no NO2 because it's a product. So unless you're told otherwise, assume that there's zero product at the beginning. And now you're being told to solve for these other equilibrium concentrations and Kc, given that at equilibrium, NO is found to be 0.2 molar. Okay, so I'm going to take all that information and set it up in an ice diagram. Now, sometimes these are called rice diagrams. They put an R at the top here because this is the reaction, and then you do initial change in equilibrium. But I like to call them ice diagrams because then I get to listen to Ice Ice Baby. Anyways, I digress. If we plug in the values that we're given with, we got 0.3 moles of the NO, we've got 0.3 moles of O2 at the beginning, and 0 of our product. At equilibrium, I've got 0.2 of NO, and therefore the change was minus 0.1. If I look at the mole ratio of this reaction, it is 2 to 1 to 2. 2, 1, 2. Okay? So that means that this is changing. This has to change twice as fast as this one, but they're both going to go down because they're both reactants. And this has to go up, but also it has the coefficient of 2, so at a 2x change. So the first reactant and the last reactant are going to change at the same rate in opposite directions, or the first reactant and the product. And the oxygen is only going to go down by half as much because that's how its coefficient works out. If you don't believe me, I'll show you in class with some models just so that we see that this is the case. But they have to follow these mole ratios in terms of how quickly they are used up or produced. So we know that NO went down by 0.1. Therefore, negative 0.1 must be the same as negative 2x. So I'm just, I already had the simple number. Now I'm setting it up equal to the change based on the coefficient. Therefore, x equals 0.05. So now if I plug 0.05 in for x across the board, I get minus 0.1, I get minus 0.05, and I get plus 0.1. And applying those changes, I get my, well, first of all, I get the equilibrium concentrations for these two, which is one of the things I was asked for in the question. So 0.25 mole per dm cubed for oxygen at equilibrium, 0.1 mole per dm cubed for NO2 at equilibrium. And now I can plug them into the Kc expression, remembering that certain concentrations have to be squared because of those 2's. But when I plug them in, I get this out as the Kc value. A couple tricks to watch out for. I'd say it's not very common, but you know the IB always holds a couple tricks up their sleeves. The key with the ICE calculations and the Kc expression is that you're supposed to plug in concentrations. Okay, so these brackets represent concentrations, which means the unit is mole per dm cubed. So when you're doing equilibria that are in the gas phase, sometimes you'll be, instead of just being told a concentration, you'll be told a number of moles, and you'll be told a volume of a container. Like if you look at this last one, that's what I did here. In a 1 dm cubed container, you have this many moles of NO and this many moles of O2. So that was a nice example. If you're given a volume of 1 dm cubed, then all of your mole amounts are really the same number as they would be for concentration, because it's 0.3 moles in a liter in a dm cubed. So that's a 0.3 mole per dm cubed for NO. So that's how it normally will be, so don't overstress about this. But if for some reason they wanted to be extra sneaky and they said you've got 0.8 and 0.4 moles in a 2 dm cubed container, well, now the actual concentrations are, those numbers have to be halved. So 0.4 and 0.2 become the concentrations respectively. They could do something similar if you're doing equilibrium that's in aqueous solution. Normally they're just going to give you all the concentrations in moles per dm cubed. That's by far the norm. But let's say you mix 50 cm cubed of a 0.1 molar solution and 50 cm cubed of another 0.1 molar solution. Well, now you've got these two solutions and the total volume has become 100 cm cubed. So pay attention that you started at 50 cm cubed for each, and now they're in a combined volume of 100. So therefore, each concentration is going to get half, because each concentration is getting diluted by mixing them and making a bigger total volume. So the actual values that you'd want to use in your ICE diagram and in your calculations would be 0.05 mole per dm cubed. So these little tricks are, again, I stress they're not very common. It's not really the major thing to worry about, but it's about reading questions carefully and showing that you truly understand that concentration is moles per dm cubed. And so depending on the volume of the container or the total volume of the solution, when you mix things, that does, according to the math, change the initial concentration. Otherwise, that's the end of the equilibrium topic, doing these ICE diagrams, doing these ICE calculations. And there's some more practice for us in class.